The most important but the most incompletely understood concept in all of science. Part 3 focuses on an example analysis of the experimental data for the heat flow in an isolated system to illustrate the origin of the second law of thermo and the maximum entropy principle of thermodynamic theory, which states that every system in nature tends to possess the maximum entropy possible under the given conditions. In part 1a of this video series, I mentioned that in 1850, Clausius published the verbal statement of the second law of thermo as heat naturally flows from hot to cold. He was not at all satisfied with this innocuous sounding statement as he compared it with the elegant first law statement, namely, energy of the universe is conserved. As a result, he started to perform a detailed analysis of the experimental data with a view to figuring out what might be hidden in the data. To illustrate his analysis, let us consider the following experiment. A 100.00 gram aluminum block is dropped into 50.00 gram sample of water in a heat insulated container. The two are at different initial temperatures. Heat spontaneously flows from the hot one to the cold one until thermal equilibrium is reached between the two. The final equilibrium temperature is some intermediate value determined by their initial temperatures, masses, and specific heats. The table shows the experimental data obtained in 6 trials of such an experiment. In the first 3 trials, aluminum is hotter and water is colder, and vice versa in the next 3. Heat spontaneously flows from the hot to the cold until at the final equilibrium state, the temperatures of both aluminum and water are the same. In each trial, Q hot equals negative Q cold and Q equals ms delta T equal to ms times T final minus T initial, where S is the specific heat, namely the amount of heat required to increase the temperature of 1 gram of the substance by 1 degree Celsius or 1 Kelvin. Thus, the value of T final is controlled by the values of M, S, and T initial for both the hot and cold bodies. T final is experimentally determined in each of the above trials as the table shows. It was to make sense of, understand, and explain data similar to these that Clausius performed an analysis of such data. The questions that automatically arise are: why does heat spontaneously flow from the hot body to the cold one and not from the cold body to the hot one? Why is a state of thermal equilibrium reached, and why does the process not continue any further? He attempted to figure the answers. More importantly, he wanted to see if the analysis would point to the existence of any numerical pattern in the experimental data that would lead to the mathematical statement of the second law, whose absence in his 1850 paper made him very dissatisfied, as was mentioned in part 1a of this video series. For our example analysis, we will consider the data in trial 3. In trial 3, aluminum is hot at an initial temperature of 59.50 degrees Celsius, equal to 332.65 Kelvin, and water is cold at an initial temperature of 28.25 degrees Celsius, equal to 301.40 Kelvin. Clausius noticed that a numerical pattern exists in the data only if Kelvin temperature is used instead of degrees Celsius. So, it is critical to first convert the initial temperatures and the final temperature from degrees Celsius to Kelvin. The final temperature in trial 3 is 37.65 degrees Celsius, equal to 310.80 Kelvin. The analysis is performed by imagining the overall process to consist of many stages. Each stage can be imagined in one of two ways. In the first approach, we consider a fixed, reasonably small change del T in the temperature of either aluminum or water at each stage of the heat flow in trial 3. We can then calculate the corresponding amount of heat transferred to the other. Using this, we can calculate the change in T, that is, del T of the other. In the second approach, we consider a fixed small amount of heat, del Q, to flow from aluminum to water at each stage of trial 3. We will first discuss the first approach in detail and use it to illustrate the origin of the first part of the mathematical statement of the second law of thermo, namely delta S total is greater than 0 for a spontaneous process. We will then discuss the second one in detail and use it to illustrate the origin of its second part, namely delta S total is equal to 0 at the equilibrium state, as well as the maximum entropy principle, although we can use either approach to illustrate both parts of the second law. Let us say that at each stage, a small change in T equal to 0.100 Kelvin occurs in the temperature of the aluminum block. That is, del T for aluminum equals negative 0.100 Kelvin. Del T refers to a reasonably small enough change as opposed to dt, which represents an infinitesimal change, namely very, very small change, and delta t that refers to a large enough finite change. The amount of heat del Q released by aluminum at each stage equals ms del T. The specific heat S of aluminum is 0.900 joule per gram Kelvin and its mass is 100.00 gram. Therefore, del Q turns out to be 9.00 joules, which is absorbed by water at each stage. Therefore, given that for water M is 50.00 gram and specific heat S is 4.184 joules per gram Kelvin, its del T is positive 0.04302 Kelvin. The magnitude of del T for water is smaller than that for aluminum, although the mass of water is smaller because it takes only 0.900 joule of heat to change the temperature of aluminum by 1 Kelvin, whereas a much larger amount of heat, namely 4.184 joule, is needed to change the temperature of water by the same 1 Kelvin. Next, we need to calculate separately for both aluminum and water the Clausius mysterious ratio of heat over Kelvin temperature mentioned in part 1, which is del Q over T equal to ms del T over T at each stage I of the process, as well as its sum from stage 1 up to the given stage I. Table 2 shows the results for aluminum. As seen in the last row of column 4, the final sum from stage 1 to the last stage at which the equilibrium state is reached happens to be negative 6.1053 joule per Kelvin for aluminum. Table 3 shows the results for water. As seen again in the last row of column 4, the final sum from stage 1 to the last stage at which the equilibrium state is reached is positive 6.4146 joule per Kelvin in this case. A graph is then drawn between ms over T on the y-axis and T on the x-axis for water. The idea here is to see the individual steps involved in the graph, but Due to the smallness of the delta value, it is hard to see the individual steps if the full temperature range is included on the x-axis. Therefore, a blown up version where the steps can be seen clearly is shown between just 305 and 306 Kelvin alone for water. A similar graph is shown for aluminum. In this case, the x-axis is the corresponding temperature range between 324.25 and 322.05 Kelvin. That is, when the temperature of water is 305 Kelvin, that of aluminum is 324.25 Kelvin, and when that of water is 306 Kelvin, that of aluminum is 322.05 Kelvin. From calculus, one may recall the concept of Riemann sum. Accordingly, imagine a rectangle under each step which goes all the way down to the x-axis for which y equals 0. Its length equals ms over t and the width is del t. Therefore, its area equals ms over t times del t. Since ms del t equals del q, this area is equal to del q over t, which is the mysterious ratio for the given stage. The sum of the areas of all such rectangles between the initial temperature and the equilibrium temperature is approximately equal to the area under the curve of ms over t versus t. This is an approximate overall value of the mysterious ratio for aluminum and for water during the spontaneous process of heat flow between them. This is shown in the last row of column 4 in table 2 for aluminum and table 3 for water. For aluminum, it is negative 6.1427 joule per Kelvin from table 2 as mentioned before. For water, it is positive 6.4244 joule per Kelvin from table 3 again as mentioned before. Clausius added the two Riemann sums and always obtained a positive value for every trial in every relevant experiment. This value for trial 3 of the experiment discussed here is positive 0.2817 joule per Kelvin. Thus, he noticed a numerical pattern in the experimental data after a detailed analysis which points to the existence of a law of nature. Yes, as was indicated in part 1, the mathematical statement of a law of nature always tells us the quantitative numerical pattern recognized to exist in relevant experimental data. For illustrations of experimental data and the numerical patterns in them for all the laws discussed in chemistry, see my book titled Understanding Chemistry with the subtitle by using scientific method as a unifying thread. The details are also forthcoming in my next YouTube video series on scientific process. Everyone with a knowledge of Riemann sums knows that if we keep decreasing the value of del T further and further, we would get more and more exact value for the area under the curve. In other words, the values would approach a limiting value. Table 4 shows some sample results for certain arbitrarily chosen values of del T for aluminum. It can be seen from the difference in the consecutive values of the total of the sums of del T over T for aluminum and water shown in the last column. This total approaches a limiting value. It also implies that the sums of del T over T for both aluminum and water separately also approach their corresponding limiting values. Notice the unacceptable negative value for the total of the two sums in the case of del T for aluminum equal to negative 2K, and the positive values for negative 1K and negative 0.5K are considerably off from the other smaller values for del T. Thus, it is important to choose small enough values for del T during this analysis. The corresponding exact area under the curve can of course be calculated using the technique of integration. The definite integral from T initial to T final of ms over T times dt yields the exact area. Here, del T, a reasonably small change in T, is replaced with dt, an infinitesimal change in T that calculus is concerned with. Since ms is a constant, it is taken outside the integral. The indefinite integral of dt over t is ln t. Therefore, the definite integral and hence the exact area under the curve is equal to ms times ln of tf over ti. The result is applied to both aluminum and water. In the case of aluminum, the exact area is negative 6.1147 joules per Kelvin. Compare this with the sum equal to negative 6.1150 joules per Kelvin obtained for del T of aluminum equal to negative 0.001 given in the last row of column 2 in table 4. In the case of water, it is positive 6.4248 joules per Kelvin. This is the same value for del T of water equal to plus 0.000430 Kelvin in the last row of column 3 in table 4. The limiting value of the total of the above two sums is positive 0.3101 joule per Kelvin. Compare this with the value of positive 0.3098 joule per Kelvin in the case of negative 0.001 Kelvin for the del T of aluminum in the last row of column 4. Del T of aluminum equal to negative 0.001 Kelvin happens to be a reasonable value for dt. So, the important question that arises here is, what exactly do the sums of del Q over T for aluminum and water separately represent in nature, and what does their total represent? Facing this million-dollar question, Clausius had to frame a postulate of thermodynamic theory. Given the significance of the mysterious heat over Kelvin temperature ratio, Clausius felt that it pointed to a change in some yet unknown state property or state function of a substance. He considered it to be similar to the internal energy U for any system that had already been postulated to exist in nature in order to replace by delta U the constant in the numerical pattern of Q plus W equal to constant recognized in the corresponding experimental data. He decided to use the limiting sums, namely negative 6.1147 joules per Kelvin and positive 6.4248 joules per Kelvin for the changes in this state property of aluminum and water respectively. Recall that these limiting values correspond to an infinitesimal change dt at every stage of the process, and it is known that such a process is nothing but a reversible process postulated by the father of thermo, Sadi Carnot, in 1824. Their total then represents the total change in this state property of the whole isolated system. Therefore, in his 1865 paper, Clausius postulated that every substance possesses a state property that he decided to call as entropy. He coined this term in a way it rhymes with energy, and he wanted to have a Greek root for it so that it can be adopted in all languages. The root is entropia, meaning transformation, since he used his analysis with the data for heat engines also, where heat is transformed into work when the engine operates between two different temperatures, and where he observed the same numerical pattern to exist. Notice that The heat engines were a very hot topic then, and Sadi Carnot had introduced the idea of reversible process during his theoretical attempt to calculate their maximum efficiency. As the next step, Clausius defined the infinitesimal change in entropy of the system, ds system, to equal d/q reversible over t. d/q and not dq is used because q is a path function, not a state function. d/q reversible represents an infinitesimal amount of heat absorbed or released by a system at each stage corresponding to an infinitesimal change dt when the process between the initial and final states is imagined to take place by a reversible path. The corresponding definite integral between the limits of t initial and t final yields delta S system. Thus, delta S system is equal to ms times ln of tf over ti, which we used earlier to calculate the exact area under the curve of ms over t versus t for an isothermal process during which t is constant. Delta S system is equal to q reversible over t equal to ms delta t over t. Therefore, delta S aluminum equals negative 6.1147 joules per Kelvin. Delta S water equals positive 6.4248 joules per Kelvin, and delta S total is positive 0.3101 joule per Kelvin, as we calculated earlier. In this manner, Clausius was able to express the mathematical statement of the first part of the second law as delta S total is greater than 0 for any spontaneous process, such as the spontaneous heat flow between aluminum and water. It is important to keep in mind that Clausius postulated only the limiting sum of del q over t, which corresponds to the infinitesimal dt constituting the imaginary reversible path, as equal to the delta S system, and not any of the other sums, such as the ones corresponding to del T of aluminum equal to negative 0.1, negative 0.05, etc. His assumption is found to be working well so far in explaining all the relevant facts, and hence we have accepted it so far. Even though in the macroscopic world spontaneous processes take place by an irreversible path, delta S system should always be calculated only by imagining a reversible path between the same initial and final states. The result so obtained for the reversible path is then applicable to any irreversible path between the same initial and final states, since S is a state function. Now, we will take up the discussion of approach number 2 in this analysis and apply it to the same trial 3 of the heat flow experiment. We imagine that the aluminum block releases to water a small amount of heat, del Q equal to 1.000 joule. Thus, del Q aluminum is negative 1.000 joule and del Q water is positive 1.000 joule. Since del Q equals ms del T, we can calculate the value of del T for both aluminum and water. They happen to be negative 0.01111 Kelvin and positive 0.004780 Kelvin respectively. To calculate the temperature at any given stage I, we algebraically add the del T value to that at the I minus first stage, that is the previous stage. In trial 3 of this experiment, the aluminum block happens to release a total amount of heat equal to 1966.48 joules to water from the beginning until the equilibrium state is established, and therefore there are 1967 stages to consider, since each stage corresponds to a transfer of 1.000 joule by aluminum to water. However, just to see theoretically what would happen to the entropy change if the heat flow had continued beyond the equilibrium state, we will consider many more stages of 1.000 joule heat transfer, each by aluminum to water. This is, of course, a special advantage of theoretical calculations as opposed to the experimental observations, and we will exploit it here. We arbitrarily choose a final temperature of water equal to 320.0042 Kelvin. The corresponding temperature of aluminum happens to be 289.4056 Kelvin. From the beginning up to this arbitrary final state, there are 3,893 stages, constituting a total transfer of 3,893 joules of heat, out of which 1966.48 joules get actually transferred, and the rest happens only in our imagination. Now, we first calculate the mysterious ratio del Q over T for stage I separately for aluminum and water as their T's change. Then we calculate the corresponding sum for stage 1 through stage I. This sum represents the sum of all del S's occurring from the beginning through stage I. Table 5 shows the results for aluminum from its initial temperature of 332.65 Kelvin up to its final temperature of 289.4056 Kelvin. Table 6 shows the results for water from its initial temperature of 301.40 Kelvin up to its final temperature of 320.0042 Kelvin. Next, we plot the total of the two sums, namely sigma del Q over T for aluminum and sigma del Q over T for water versus T water. T water is arbitrarily chosen here and T aluminum is an equally valid choice also. It can be observed that this total keeps increasing from the initial temperature to the equilibrium temperature, reaches a maximum at the equilibrium temperature, and then keeps decreasing. This analysis then clearly indicates that it would keep decreasing in case the heat flow had continued beyond the equilibrium state. The same kind of graph is obtained if one considers dt corresponding to the reversible path instead of del T. Thus, delta S total for aluminum and water taken together keeps increasing initially. In other words, S total keeps increasing as more and more heat flow occurs from the hot aluminum to the cold water. It reaches a maximum at the equilibrium temperature, after which it does not change in actuality. This became the maximum entropy principle of thermodynamic theory, which states that every system tends to possess as maximum an entropy as possible under the given conditions. As to why we use the phrase tends to in this statement, see part 1b of this video series. That delta S total does not change any further as the equilibrium temperature stays constant implies that delta S total equals 0 once the equilibrium state is reached during this irreversible spontaneous process. As Clausius noticed the same pattern in all relevant experimental data, this became the second part of his mathematical statement of the second law. That is, delta S total equals 0. Both parts he stated together in the corresponding mathematical statement of the second law of thermo as delta S total is greater than or equal to 0. Here, the greater than symbol, of course, corresponds to the spontaneous process, and the equal to symbol corresponds to the equilibrium state. This, he felt, is as succinct and elegant as the mathematical statement of the first law, delta U equals Q plus W, which he had published in his 1850 paper. Since in the above analysis, water and aluminum together form an isolated system in a heat-insulated container, the second law of thermo can also be stated as delta S isolated system is greater than or equal to 0. In any isolated system, energy stays constant and hence a spontaneous process can ever take place only if the entropy of the system can thereby increase. Otherwise, it would never. He gave a verbal statement of the second law as entropy of the universe is increasing. This was in parallel with his first law statement, namely, energy of the universe is conserved, which he had published in his 1850 paper. In 1850, he desired to give as elegant a verbal statement for the second law as his first law statement, and he did achieve it. His implication is that in the universe, spontaneous processes keep happening all the time, and as a result, its entropy must keep increasing. After he formulated both his mathematical and verbal statements of the second law, he, of course, must have been the happiest as opposed to his mental state in 1850 when he could publish only the verbal statement of the second law, as heat naturally flows from hot to cold, which sounded so innocuous to him, lacking a mathematical form to it. What a feat indeed! The only thing is that, as was mentioned in part 1a, Clausius could not figure out what exactly his postulated state property of entropy represented. After about 15 years, it was Bottzmann who elegantly explained what exactly entropy is. We discussed his interpretation in detail in parts 1 and 2 of this video series. Finally, a word of caution regarding the use of the term universe. There is a misconception that is quite prevalent. It springs from Clausius's use of this term in his verbal statement of the second law. There are popular books and some websites which use delta S universe in place of delta S total and state that delta S universe increases in the given experiment. It is important to realize that in any experiment that we perform, we always deal with only the immediate surroundings of the system in question and never with the rest of the universe as its surroundings, since it is only its immediate surroundings that interact with it. Such immediate surroundings are indeed a very, very small portion of the rest of the universe. Therefore, it is not appropriate to use delta S universe with respect to any given experiment. The appropriate one is delta S total to refer to the change in the total of the entropies of the system and its surroundings that interact with it. I wholeheartedly thank you all for watching all the videos in this video series.